So theorem 1, it says the tangent at any point of a circle is perpendicular to the radius through the point of contact. So what is given the theorem is a circle with center O and a tangent xy to a circle at a point P, right? And we need to prove that OP is perpendicular to xy. OP is perpendicular to xy. So as you can see, there is a diagram here. We need to prove that OP is perpendicular to the line xy. Okay. Now, what the constructions we made here is take a point Q on xy. Take a point Q on xy. This point Q on the line xy other than P and join this OQ. Join OQ. This is the construction we have made. Okay. Now let's see how we prove it. So yeah, this is the statements column and this is the reasons column. Okay, so statement says the first statement among this is the point Q must lie outside the circle. I'm telling the point Q must lie outside the circle. Why is it so? Because if Q lies inside the circle, then xy will become a secant and not a tangent of the circle, right? So that's the reason. We can directly, by looking at this diagram, we can easily say that the point Q must lie outside the circle. Okay. Then coming to the next point, therefore OQ is longer than the radius OP of the circle. That is, OQ will be greater than OP. Correct? OQ will be always greater than this line OP. That is the second statement. Then the third point, OP is the shortest of all the distances of the point O to the points of xy. Correct? Because whenever this happens for every point on the line xy except the point P. So other than P, if you take any point on this line xy, it will be always shortest. The line OP will be the shortest of all these straight lines, right? And in this case we have the line OQ, right? So that's the reason we can easily say that OP is perpendicular to xy. Since OP is the shortest of all the distances of the point O to the points of xy, we conclude that OP will be always perpendicular to xy. So this completes the proof. Let's look at the another theorem in this chapter. Theorem 2, it says that the lengths of the tangents drawn from an external point to a circle are equal. Okay, so what is given the question? Given the theorem, a circle with center O. Okay, there is a circle with center at O, a point P lying outside the circle, and the two tangents are there, PQ and PR, on the circle from the point P. This is what is given in the theorem. Then what is to be proved is the lengths of PQ and PR are equal. We need to prove that they are equal. Okay. Now construction is we need to join OP, OQ and OR. Alright. So this is how it is. See, PQ and PR is equal. We need to prove. Now we will join all this OP, OQ and OR. Okay. After doing this construction, we will prove. Now, so there are two columns, statements, and the other one for reason. Okay, so as we can see that this angle will be 90 degrees for both these triangles, right? So that means these two are right angle triangles, right? So in right angles, OQP and ORP, in OQP and ORP, OQP and ORP, right? So what we have is OQ is equal to OR. OQ and OR are equal because they are the radii of the same circle. That is our first statement. And the second statement, OP is equal to OP. OP is the common side for both the right triangles, right? That is of the common side. Hence, by using the RHS rule, we can easily say that the triangles OQP and triangle ORP are congruent to each other by using RHS rule. Okay, since they are congruent, we can easily say that the lengths of PQ and PR are equal by using CPCT. CPCT means corresponding parts of congruent triangles, right? According to this rule, we can easily say that PQ is equal to PR. Okay, hence the proof.